Welcome back to Python tutorial 5 of the course time dependent quantum chemistry. We have gone over just how to normalize the initial wave function, and we will proceed further to check how to now time propagate numerically. That is a very simple procedure we will follow. The time propagation part will be done through the split operator approach. So, we have already realized and we have also found the recipe for implementing the split operator method, which propagates the wave function from t equals 0 to some other time. So, this is my initial wave function, which I have already discretized and normalized it, and this is your final wave function after time t. And the way it is done is we make a short time propagator like delta t short time propagation, and then we just keep propagating it in an iterative process. So, what does it mean? I start with this function, and the recipe we have already discussed is that we start with this wave function, we do a Fourier transform to convert it to the momentum domain. In the momentum domain, I employ the kinetic energy operator, and so then we come back to the position domain, and then we keep repeating. So, delta t propagation will be repeated until I reach the final time. So, that is the basic idea. We have already developed it. Here this sign is, we have never used this sign before. This is nothing but the n times product that we have seen already. We have to do this n time this short time propagation n times. So, this is called n times product. That is all. It should not puzzle anybody. Now, recall that for each time in the product, the potential part of the propagator is carried out in the position space. So, we just remember that we said that this is the potential part, and these two are the kinetic energy part. So, this is the symmetrized product of the split operator approach. We have seen that initially this part has to be acting on this, then this part will be acting on the resultant part, then this part will be acting on the resultant part. But when I am employing this potential part, the potential part has to be carried out in the position space, and the kinetic part of the propagator is carried out in the momentum space. That we have already understood. If you need recapitulation, you please go ahead and check the split operator approach, the module which is covering split operator approach. So, with this idea, in atomic unit we have already considered that h cut equals 1. So, this part, this h cut, I can eliminate if we consider atomic unit. And for the free particle, we have considered, because it is a free particle, we can consider v. This is not velocity, this is the potential, this is the potential. V is 0, because we are dealing with zero interaction potential, that is called free particle. So, in that case, if we do that, then in that case under atomic unit and free particle, for the free particle, this entire expression becomes like this: n time products of e to the power minus I t delta t. This is the time propagator I have, and then psi x 0. This is what we have, and that is exactly needs to be repeated here following this scheme. So, explicit numerical steps are summarized here. We start with the initial wave packet, which is the x psi x 0. Then, because we have to carry out the kinetic energy part in the momentum domain, k domain or p domain, both are equivalent. Their expressions are different, but they are equivalent. So, we have to convert this one to momentum domain, and that conversion can be done through fast Fourier transform. We are now familiar with it. We will see the implementation again, and then we have to carry out this kinetic energy part and get an another wave function which is displaced to this time delta t. So, after delta t time we have now the wave function in the momentum domain. Then we have to inverse Fourier transform to the position domain. This wave function is now new wave function for the feed to the next iteration, and this needs to be iterated until I reach the final time. That is the basic idea, and final time is going to be n delta t time is the final time. So, n times I have to repeat this one. Here this psi x x0, this represents the initial wave function. And this one represents a new wave function at time t plus delta t, sorry, 0 plus delta t, 0 plus delta t. So, delta t time has been advanced for this wave function. To implement this product recipe, this iterative product recipe, the sequence is repeated with the help of a for loop. So, we will use a for loop to repeat this one for every delta t with psi dash. This psi dash will be serving as the new initial wave function for the next iteration of the loop. So, we will use the for loop for implementing this one. We must select and sufficiently small delta t, that we have also understood why we should select this very small delta t to achieve higher accuracy in this computation, because the split operator approach is an approximate approach and the error goes with like this. So, higher order errors will be neglected if the delta t is small. And the kinetic energy operator on the K grid is represented by, so there is a kinetic energy operator here T. So, this kinetic energy operator will be represented by, as I have mentioned previously, in atomic unit it is going to be half K naught square, half K square, because it is for any K. So, what is the kinetic energy? It is more like a K dependent function depending on what K I have. And so in the K domain I have the there is a K domain I have created, discretized K domain, and for each K I have a kinetic energy operator. So, what we can see that kinetic energy in the K domain is actually quadratic in nature, and quadratic in nature, which means like this. It spreads out between both both sides of the 0. So, it is quadratic in nature in the momentum domain, and it should be half K square, because in the atomic unit. So, we will express it like 0.5 K square. That is the kinetic energy of the kinetic energy operator in the K space. So, we will go ahead and check the function now. We will move to laptop and implement this. So, the first few lines will be kept here. From SciPy we have to import the same square root functionality, arrange functionality, exponential functionality. In addition to that, I will also import pi, and there is a reason why we are importing pi, because for preparation of the K grid I need this pi. From integrate I have to import again Simpson's method, and then I have to because we will make use of Fourier transform, we have to import some functionalities from SciPy FFT pack submodule, SciPy FFT pack submodule, import FFT frequency, FFT and IFFT. These are the functionalities we are going to import. And then remaining part, matplot library will help us plot the function, and creating the x grid remains to be the same. We have the x grid, then we have to define the define and normalize the initial wave function, that we are keeping the same, is a traveling Gaussian. And then we have the normalized wave function, and once we have the normalized wave function, we can write down probability of PSI norm, probability density initial. So we will compare with the initial probability density. Probability density is nothing but absolute value of this PSI norm square. So we are writing this one because we would like to check the probability density. We would like to plot initial probability density and the final probability density after the iteration. Now we'll go to the important step, the iteration, how we are going to start the iteration. But before we start the iteration, time propagation, we have to create the k space first, because we need to change to k space to carry out the potential part, kinetic energy part of the split operator component. So we will write down time propagation implementing split operator approach, n equals length of x. I need to know that, because when you define k, I will define k by 2 pi multiplied by the frequency components, FFT frequency components. For that I have 2 inputs, n number of grid points I have in the x space, as well as the separation of grid points. These are the 2 things, and this is the way we create the k space. And then I am going to define the kinetic energy in the k space, and that definition is very simple. It is going to be 0.5 multiplied by the k, each k square. So this is the definition of the kinetic energy, defining the kinetic energy. Once the kinetic energy definition is over, then I can now define the NT. Now NT is total number of steps I am going to carry out. This is going to be total number of steps. And each step size dt is taken to be 0.1. So note that if I take dt to be 0.1, what is the unit? It is in second? No, it is in all in atomic unit. So dt is the time step, it is taken to be atomic unit of time. Here x is taken to be 0.2, which is the separation. 0.2 is in again atomic unit of length, and that's the way we are moving. So these are presented in atomic unit. Now I am going to implement the for loop for the iteration part. So the way we are going to implement the for loop, it is going to be I in arrange functionality. This is something which we know. Arrange, for arrange functionality, we generally we need 3 inputs. One is starting point, end point, and the division. But arrange functionality, another format of arrange functionality is there. It is going to be it is the end point of this. In that case, if we use this arrange functionality with single input, it means that a single input is considered to be the endpoint, and definitely endpoint will not be considered. So it will be considering only the point before the endpoint. But what it will be giving you is the it will be giving you the numbers separated by 1. So it will start with 0, then 1, 2, 3, 4. It will continue until it reaches 99. So how many iterations it will undergo? It will undergo 100 iteration, but it will start, the index will start, the index is actually here I, index will be starting from 0 and it will end at 99. So that's the basic idea. So the first thing in this iteration we are going to do is that first we have to Fourier transform the wave function, Fourier transform of the wave function. When you do the Fourier transform wave function to K space, when you do the Fourier transform of the wave function, we get that PSI norm, PSI norm, we get PSI norm in the Fourier space, which is nothing but FFT of PSI norm. So PSI norm underscore k is representing the wave function in the Fourier domain. Then I have to use the time evolution. We have to carry out the kinetic part of the split operator. Here only we have kinetic part, so split operator is nothing but the kinetic part only. There is no potential part. That I can carry out like this way. I name it Ke equals, it is going to be exponential of minus 1.0 j multiplied by kinetic energy multiplied by dt. That's the kinetic energy part of it. This part will be multiplied by the Fourier transform part. So this is scalar multiplication. So each point will be, each is element wise multiplication for this. So note that K underscore k, it is an array, and this array, when you multiplying by dt and minus ij, which is the complex number, it is giving you another array with this multiplication, element wise multiplication. So this entire thing is an array. This array is multiplied by this array, which means that I am element wise multiplying it and then getting the another array. So this is again another array. So this is the way we have performed the time propagation delta t, and then what we need to do is that IFFT, inverse Fourier transform of the wave function to real space. And for that, all we need to do is I will write down PSI norm. Again, I am going to update this one. So here I start with this PSI norm. The iteration is started with PSI norm. When the iteration is started in PSI norm, you check this. PSI norm is actually a normalized wave function, this one. I start with it. But when during the iteration, this PSI norm will be updated. So in the second iteration, after the first step, the second iteration, this PSI norm will be updated to this PSI norm. So that's the way iteration continues. So I am now updating the PSI norm value IFFT, which is nothing but IFFT of this function. So in the end, so this iteration will continue until NT is satisfied, this until the end point of this array, NT array, and and then once it is satisfied, finally I get PSI norm, the updated value of the PSI norm. That is the, so I'll find out the probability density final, which is going to be nothing but absolute value of the final updated PSI norm. And now if I plotting everything, it would be easier to visualize what I am doing, plotting the initial and final probability densities. Plot x versus initial probability density plot x versus final probability density. These are the two plots I will have, and because I have already done this problem, I know the limit should be set to be for better visualization. That's all. So we can run the program, and we see that the initial probability, which was centered at 0, that is quite expected. This is a 0, which means the 0 length, which means the in atomic unit. So it was centered at 0. It was normalized wave function. Probability is normalized. So the probability, so the initial probability or the center of the probability was at x equals 0. But after time t, what is the time I'm looking at? Nt equals 100. So after 100 atomic unit of time, what I get? The probability is centered almost near 10. So probability is moving, and when the probability density is moving, it means that there is a quantum dynamics, and that's the way we represent the quantum dynamics. So we will move to the slides now, and we will see that this entire protocol has been implemented through this through this split operator approach. Now, couple of things can be interesting here to note. Again, is that these steps we are these steps can be one more time clarified. Here we are considering NT to be 100 atomic unit of time. After 100 atomic unit of time, where the probability density is, and that's the final probability density we have found. So this is something which you should remember, that, and the delta t we have taken to be 0.1 atomic unit. And one more thing we have to remember, that in the beginning of the iteration, we have this PSI norm, normalized wave function, that is used here. But then, so that is used here in the first iteration, but then this PSI norm will be updated, and that's why you have kept the same name, and it will be keep iterating until I get this 100 step over. The moment 100 step is over, then I get the probability density as a final probability density. So this is the major step. One can take a look at this part. This is the time propagation part, how we are doing this time propagation. As you can see that the kinetic part of the propagator has been implemented or carried out in the momentum space only. So with this, we see that the center of the Gaussian is moving, and as center of the Gaussian is moving, and not only that, it is spreading out also, and its amplitude is going down. It's spread out, and so this is the quite natural expectation for the particle, a free particle, what we have already concluded from analytical approach previously. Now we want to be little more quantitative in the sense that we can test Arrhenius theorem. Arrhenius theorem suggests that the expectation value will follow the it will follow the classical trajectory. So a Gaussian function, if I have a Gaussian function like this, it is characterized by its center position and its width. Both are important characterization of the Gaussian function. So this suggests the spread of the Gaussian distribution, and this shows the mean position or the expectation value. Of the Gaussian. So this is the Gaussian distribution, and we in general express it a e to the power a x square. That's the way we express it. So this Gaussian distribution is centered at x equals 0, and its width is given by delta x. Although delta x is not defined with respect to the wave function, it is defined, remember, it is defined with respect to probability density distribution. So if this is the wave function, then probability density distribution looks like this: e to the power a square e to the power minus 2ax square. In this distribution function we define delta x. This is something which we have emphasized previously also, and this delta x has many ways you can define the delta x. It can be full width half max, or it can be full width half max. What does it mean? It means that the width where the intensity has dropped down the half of its maximum intensity, that is called full width half max. So that's the way in the spread of the of a Gaussian function can be described. And if we describe it as a full width half max, then we get immediately, this is also we have seen, this a equals 2 ln 2 by delta x square. That's we get it. So full width half max delta x is defined with respect to its distribution function, not with respect to the wave function. This is something we should remember, that's the convenient this is the standard procedure we follow always, and based on that only we defined a equals this one. Now in different context, when you deal with Gaussian distribution, it is the width is also expressed in terms of its variance, and that is defined by x square minus x square, like this. It is the variance, and if we look at that variance, so what is this x square? This is the expectation value of x square, which is nothing but minus infinity to plus infinity psi x square dx. That's the value, that's the expression, and expectation value of x is given by minus infinity to plus infinity psi x dx. That's the way expectation value of x is given. So graphically, if we think about it, so this is what we get from expression, that mathematical expression, and from this mathematical expression we get this sigma. But sigma is actually, I told you, sigma is representing some kind of spread of the Gaussian distribution. And what is that spread? It's showing, in general, one can use a simple math and can show that this sigma is actually representing the half width sorry, this is here. Sigma is representing, this is the sigma. So, sigma is representing half width, it is not the full width, just like this, it is not like full width, it is the half width at almost 60% of the maximum. So, this is actually 60% of maximum. And one can prove it very easily the way we have calculated full width half max, similar way one can calculate it and one can prove it. And in that case the Gaussian distribution takes this following form, a e to the power minus x square by 2 sigma square. Gaussian the wave function takes this form in terms of sigma. So, sigma which can be calculated analytically, because as long as we know the wave function, we can multiply, this is scalar multiplication, we can multiply by x. So, both arrays has to be multiplied and we can get these two values, we can subtract and get the square root of that value, I can immediately get sigma. So, sigma can be very easily calculated and it can be implemented in the Python programming the way we have learned already. And that is the reason why we are going to use sigma to describe the spread of the Gaussian distribution. But the definition, graphical definition of sigma is following. I repeat one more time. In contrary to the full width half max, what we have learned, full width half max is the full width at the half maximum. Maximum is here, so at the half of the maximum it is the width. But sigma, which is related to variance, is also representing the spread of the Gaussian, but that corresponds to the half width. This is the half width, we are not taking full width here, this is the half width at about 60% of the maximum. So, maximum is here, 60% of the maximum is here. So, full width half max is somewhere here. So, this is delta x. So, this is the difference, but still sigma can represent the variation in this. So, we will go back to this testing this entire thing in laptop right now, and we will see how it is going to can be implemented in the Python programming. So, everything remains to be the same, I do not need to change anything. These should be there, but in the end, instead of plotting things, we do not need to plot it right now. We will do one thing. So, we can remove this matplotlib library as well. Instead of plotting, what we will do, we will find out an average value. AVG1 is defined as Simpson method we will be using, and we will find out the probability density final multiplied by x comma x. So, this is your the first integration we discussed. The probability density has to be multiplied by x and then integrate over x. So, that is exactly what we have implemented here. Then another average we are defining AVG2 as the integration, and in this integration we have to multiply by x square. So, x square will be multiplied, or we can say x multiplied by x, that is also fine. So, x square will be multiplied by the probability density and then we integrate over x, and variance would be defined by square root of this AVG2 minus AVG1. These two values has to be subtracted, AVG2 minus AVG1 multiplied by AVG1. Remember, it is the it is the difference between square root of the difference between the expectation value of the x square, that is the value, and square of the expectation value of x. That's the way it is. So that's the way we have written it, and then we can print it, print width equals %f, %, this is the formatted print, %, I'm going to, width is actually the defined by the variance in our calculation, so I will write down % variance. So we have one place kept within this quote, this in this location the variance value will be inserted. That's the way it will be printing. Another thing will be printing here is that the center of the Gaussian, which is the expectation value of the Gaussian, and expectation value of the Gaussian is shown by this way, and now this slot, this %f slot will be filled by the expectation value of x, which is the average one. This is the expectation value, and we can now run the program. So if we run the program, we should delete these things because we are not defining anymore. So now we can run the program, and we see that for this 100, after the 100 atomic unit of time, we get the width and the average position. So we can keep doing it. We can change the 100 from 10. We can use anything. We can use 2 and then run it. I get the width and the center position. I can make it this was NT to be 20, and I can see that width and Gaussian center position is changing. So everything is changing. So if we keep doing it, then in the end we will go back to this slide right now, and in the end what we see is that we get some values. So what we get is that if we use the this is your time axis, and at 0 time it is at the 0 position, that is we know at 0 time and 0 position, and then the different time it's actually, so this is your x, this is your this width versus, so this axis is representing the mean position as well as the width, and width is the sigma. So both it's representing. So we can see that it's starting. So at the starting point, so this part is the width and this is representing the sigma. This is the width and this is the expectation value. What we see that the blue curve at the 0 position, it is centered at 0. So these are the points we get corresponding to x values. You can keep changing. This is actually time, but we are plotting it. This is the way one can plot further all these values, and if we plot it, we get this different time. So this is time versus width, which is sigma, and this is the expectation value of x, and we can plot it. This is something which we can do it. So after running this program for different NT, different time, I want to check at different time what is my final width and the position, expectation value of the position or center of the Gaussian. If we do that, then we get these values and we just simply plot it, and if we plot it, we see that at the 0 time, when I start the dynamics, the center position is 0. That is expected because we started with center 0, the wave function centered at the 0 position, and it's linearly changing the position. This is something we should note, because it is linearly changing. It means that if x is linear with respect to time, let's say some kind of at, if it is linear with respect to time, then dx dt representing the velocity is going to be constant, and that it should happen because it's a free particle. Free particle is not experiencing any potential. It is a zero interaction potential. If no potential is there, which means there is no force acting on that. So if there is no force on a particle, it should not change the momentum, it should not change the velocity. It will be forever traveling with that velocity only. So that is something which is very interesting to note. Second thing to note here is that sigma, the width spread, is also almost linear with respect to time at a longer time, but the initial time it is not linear anymore. It is actually non-linear. So the spread, how quickly it will be spreading, that is non-linear in the beginning, but later time it is almost remain to be linear. Linearly it is spreading out. So these two facts have come up from from this study. We will stop here, and we will look at the linear potential problem in the next session.